Today's webinar. I'm Hugo Silva from Pontificia Universidad Católica de Chile, and I'm going to present today a paper about urban road congestion management with a special focus on capacity investment. So I'm happy to take questions during the presentation, so you can write them in the chat. I'll be reading and trying to answer as soon as possible, so feel free to interrupt me. So this is a joint work with Leonardo Basso and Ignacio Riquelme from Universidad de Chile. So, as a starting point, we all know congestion is a major issue and all over the world. So, for instance, just figures from 3 parts of the world. In Santiago, in 2012, more than 30% of the workers spent more than 60 minutes in a bus only getting to their workplace. So that's at least 2 hours a day going to work and coming back home. In the US, each person spends on average 100 minutes per day in traffic, which is valued at $760 billion. In London, last year, the average speed in the morning peak in central London was 13.4 kilometers per hour, and in inner London was almost 18 kilometers per hour. So there's a congestion everywhere. It seems to be in every part of the city, independent of income, maybe Europe, the US, or developing countries. And the main reason, or one main reason for this, is that urban transport prices do not reflect marginal social cost. And the question we want to answer in this paper is about what can we do. So one option is build bigger or more roads, and another option is to manage the current road capacity. And in this category there are many options. One of them is giving priority to public transport, for instance, giving subsidies or building bus corridors. Another is to price car trips, and also you can implement driving restrictions. So today we're going to focus mainly on the road capacity investment and its interaction with the pricing policies. This is a local news from Santiago, where you can see that almost $3,000 million are going to be spent in urban highways. This is 2 years ago. So it is a solution that is being implemented, or a policy that is being implemented as a solution here. And also in the US, you can see here the amount of money the US spends in highway and street construction. So from 2002 up to 2015, it went up from $60,000 million to $90,000 million, with a recession around between 2008 and 2012. So it is a policy that is being implemented, and we want to study, well, how good is it, how efficient it is, and that's the main research question of this paper. And we're also interested in studying how does it compare and interact with the other possible policies to reduce congestion. And we're going to study the interaction with car congestion pricing, public transport subsidies, and bus corridors. So previous contributions, they start with Downs-Thomson, the 60s and 70s, in what is called the Downs-Thomson paradox. And the hypothesis is that in equilibrium, car and bus generalized costs will be equal. So in other words, they are perfect substitutes. And the consequence of this hypothesis is that increasing road capacity makes congestion worse. Everyone is worse off after the capacity increase. And let's see this graphically. So you have a total demand that is constant and is represented by the width of the horizontal axis, and on the vertical axis you have cost of traveling. So from left to right, car trips are increasing, car demand is increasing. And as there is congestion, the cost is rising. So the more cars there are, the higher the cost of traveling is. That's what the curve is representing. Now from right to left, I'm gonna draw the public transport cost. And the hypothesis here is that there are scale economies. So an additional user of public transport reduces the average cost. And this could be because of the mooring effect. So another user makes the optimal provision to increase frequency, and that reduces waiting times for everyone. So that's why the cost could be decreasing. This could also be because line density is increased, the network is bigger, so people walk less. Now the equilibrium here with these assumptions is the intersection of the curves. So that's the point where no one wants to switch modes. Everyone experiences the same generalized cost of traveling. And there's a share of car users and a share of public transport users. Now, what happens when you increase road capacity? Well, the cost of traveling by car is less. So the curve shifts to the right. So for the same amount of people traveling, same amount of cars, there's less travel time, less costs. So now, how does the new equilibrium look like if road capacity is increased? Well, you have to find a new intersection. And you can see that is to the right of the previous one. So there are more people traveling by car and less people by public transport, and the generalized cost of traveling increases. This intersection is above the previous one. So this is the paradox. You increase road capacity and everyone is worse off. Now this is the earliest contribution of to the debate from the transport side, and it has been used a lot to criticize the road capacity investment policy. Now, there are some papers that study what happens if you relax some of these assumptions. For instance, the Basso and Jaradias, if you consider that modes are imperfect substitutes, and Sang, Lindsay, and Young, if the total demand is imperfectly elastic, or there is transit crowding, or the transfer operation is not optimal from a welfare point of view, but maybe there's a private operator, and what they both find is that this paradox may not hold. So that's the recent contribution to this side of the debate. The paradox may not hold. Now, there's also an empirical literature, a seminal paper by Duranton and Turner, which they study road capacity increase in the US, 30 years of data, and they find that increasing the lane kilometers leads to a proportional increase of vehicle kilometers traveled. So the elasticity is one. And then if travel times are a function of the use capacity ratio, then they don't change. And this holds for interstate travel. Then Zhu and Zhang find something similar for Japan, where they find an elasticity of 1.2 to 1.3. But the issue with this approach is that first it is aggregate, so we don't know what happens in space of time of day. We don't know if the increase was mostly in off-peak hours or in peak hours, where the congestion problem is more severe. There is no distinction between increasing the capacity of current roads or if this was an extension of the length of the road. So new places are now have accessibility to a highway, and therefore it does not allow for comparing policies and assessing the social benefit. We don't know if it is efficient or not. We know there was additional consumption, and if travel times did not change, well, you have benefits from consumption, new consumption. And that has to be compared with the cost of providing this capacity. And that's what we're trying to do in this paper. And Well, what we have in this paper is a comparison of the road investment policy with the policy of building bus corridors, implementing car congestion pricing, and subsidizing public transport. And for this, we have a detailed demand model. We consider that public funds are costly, so there's a marginal cost of public funds. We use detailed travel times functions borrowed from the traffic engineering literature, and we try to study city effects and bus stop and pavement technology effects, which is something I'm going to explain now. First, the city effects. So in this figure, you have lots of cities, and every dot is a city, which in the horizontal axis is the GDP per capita, so the income, and on the vertical axis is the modal share of motorized private mode. And you can see clearly at least three types of city, if you want. So first, you have on the top the North American pattern, what the authors call the North American pattern, where you have lots of cities with relatively high income and very high share of motorized private mode. Then you have in yellow the European pattern, when there are many European cities with a similar income as the North American cities, but significantly lower share of motorized private mode. Then you have what they call the most efficient pattern, where there are only 4 cities, and on the left there's a group of cities that is mostly developing cities, but the income is relatively low and the share of motorized private mode varies from 10 to 50, 60%. So what we want to study, what we want to take into account is that this may have an effect, an impact on the efficiency of the policy. So is it a good policy to implement if you're a North American city, or is it the case in a developing city? Can a developing city take the path of a North American pattern on the European pattern, depending on the policies you implement? So what we want to do is to take into account differences in income and differences in initial model share when you implement a policy. And the second element that I was mentioning is the bus stop and pavement technology. So what we're gonna look is compare cases where the efficiency is low and high. And the picture shows on the left a low efficiency of bus stop and pavement technology. So you have a bus that stops, opens the front door, people only enter through the front door are paying, for instance, with cash. So queues build up, and there is congestion in bus stops. On the right, you have an efficient bus stop and pavement technology, where the platform is larger. Probably there are 2 or 3 berths or places for the buses. The bus arrives, opens all doors, and people board much quicker. So this is low versus high efficiency, and we're going to see the impact of this on the efficiency of the policies. So the methodology, first, I'm going to show you a simplified theoretical model to get some insights, and then a realistic and detailed model with simulations. And what we consider is 3 city types, but today I'm going to talk only about the European type of city. So high income and let's say 50–60% of car share trips. So here's the model. You have first total demand is fixed and is Y. Then the demand for cars, YA, is a function of the generalized price of cars and buses. That's a function H of GA and GB, so the generalized price of cars and buses. And people that don't travel by car, they take the bus. That's the first line. The second line, GB, is the generalized price of traveling by bus. The first is the access cost, which can be walking to the bus stop. The second is the fare, PB, what you have to pay. The third is the time on a bus while in movement, which depends on how many people are traveling, how many people are using the car because there is congestion, the frequency, F of the buses, and K, the capacity of the road. The fourth term, TS, is the time in bus stops, which depends on the bus demand, on the frequency, and of the bus size. And of course, of the technology, bus stop and payment technology, which we're gonna see later. And the last term is the waiting time as a function of the frequency. Then you have the generalized price of a car, is the operating cost, COA, which is mostly fuel, but it can be maintenance, tires, and so on. Then PA could be the car congestion price, which can be implemented or not. TA, the third term, is travel time by car, and the last term represents the cross congestion, so the effect of bus stop operations on cars. So what we assume is that traffic engineering literature has not yet delivered a function for this, is that cars experience only a share, epsilon, of the time that a bus spends in a bus stop. And it depends on the frequency. So if the frequency is very low, let's say 1 bus per hour, this term epsilon should be almost 0. Then 1 bus per hour does not congest cars heavily. On the other hand, if it is 100 buses per hour, then the bus stop operation is going to congest cars more severely, and this epsilon gets closer to the value of 1. That's the idea of this term. Then you have the welfare function, which we're going to optimize over prices, frequency, bus size, and road capacity. And the different policies are going to be represented by constraints to the model. For instance, subsidy could be that the revenue from bus fares covers the cost. And if PA, the car price, is 0, then there is no congestion pricing. And if it is optimized, then we're looking at optimal car congestion pricing. Now, when we solve this model, we can only identify the price difference between the two modes because there are perfect substitutes and the total demand is inelastic, is fixed. But in the simulation model, numerical model, we're gonna identify them separately. And the interpretation is just as in separate models. So this is what the optimal car congestion price should be, which is the marginal external cost, the effect of an additional car on travel times for cars and for buses, because there is cross congestion. That's what you find if you have a model with only cars, the classic marginal external cost, or Piguvian toll if you want. And then the optimal bus fare has 2 terms. First, the difference between the marginal cost and the average user cost, which is determined by the degree of scale economies. So if the mooring effect is significant, this could be negative. And the second term is the marginal external cost of buses. As we're considering congestion in the roads, then buses congest cars. The first term in the marginal external cost, and bus stop operations congest cars. And that should be taken into account in the optimal price. Now, a closer look at each of the terms. Here you have the cross-congestion effects. The first one in the red circle is the congestion a car imposes on buses, and the second one is the congestion that a bus imposes on cars. We have bus stop and payment technology effects, so the effect of an additional bus user on bus stop operations, and the second is the same, but when it affects cars. That's why it's multiplied by epsilon. Now, if you implement bus corridors, some terms disappear. So all the cross-congestion effects are no longer there, and the times functions are different when you have bus lanes or bus corridors. But the main point I want to make with this theoretical model is the effect of increasing road capacity in the optimal price. So if road capacity is very large, then the marginal congestion effects on roads will be negligible, which is the ones that are crossed there. So if those effects are negligible, then you have the second equation over there, where the car price is the bus fare minus a term, which is given by how an additional user of public transport congests buses and cars through bus stop operations. So, for any given bus fare, the optimal congestion toll may be very small. It may even hit zero. And it depends heavily on TS, which is the bus stop time. So this shows the importance of the bus stop and payment technology on optimal prices and on policies. And that's why in the numerical model we're gonna see the difference between having a bus stop and payment technology with low efficiency versus high efficiency. Now let's move on to the simulation model. This is based on a previous paper by us, by Leo Basso and me, which is public in the American Economic Journal, Economic Policy. And the main features are the following. We have the total demand is elastic, so it's price sensitive. We have two periods, peak and off-peak, and there is intertemporal elasticity. We also consider the marginal cost of public funds, so raising $1 for subsidies generates an inefficiency in some other side of the economy, and it may have, let's say, a 15% effect. So $1 of subsidy costs really $1.15. And we use the best possible engineering functions that are available to model the travel times in roads and bus stop operations and bus costs. And we're going to look at only two bus stop technologies based on a paper by Tirati. We also have, this model is a partial equilibrium model, so there is no housing decisions, no labor market, so the travel distance is fixed. And the point here to make is that this is a shorter run than, for example, the paper by Duranton and Turner, which look at 30 years of data. This means, and I want to make this point clear, that when we're looking at this is possibly more favorable for road expansion, as induced demand could be higher. So we're not modeling fully the effects of road capacity investment in induced demand. So that's something I want to make clear. Now, the demand model looks like this. We have a nested logit demand model where representative individual chooses between traveling during the peak, traveling during the off-peak, and not traveling at all. And if this individual chooses to travel in one of the two periods, he or she chooses between car and bus. And this model at the end delivers the probability or the share of people traveling by each mode in each period and the share of people that is not traveling. Now we calibrate this along with the bus cost and everything in the model that I don't have time to show you now, but it's on the paper and you can of course contact me and I'll give you as many details as you want. And for the European city, we use real data. We got the information from the main cities, the capitals of the largest capitals in Europe. And what we have is a congestion baseline scenario. So the speeds that we're going to consider as a reference case before implementing any policy are between 13 and 18 kilometers per hour, and we're going to have 2 bus stop and payment technologies. And always is going to be front door boarding. And when we compare cases, the initial speeds are going to be the same, so they're equally congested. The case A is inefficient. We have payment in cash and only 1 berth, so 1 bus can open doors at the time, and the efficient has a contactless card and 2 berths, so 2 buses can operate at the same time, every bus. And when we consider the bus corridor policy, it has at most 1 lane in each direction. So we're not considering a bus corridor with 2 lanes. Now, when we solve this numerical model and have results, they look like this. And I don't want you to look at the table much in detail, but I do want to show you that we have very detailed results, and for every case we have lots of results on speeds, shares of people, road capacity, frequencies, prices, and so on. But what I'm going to focus in the rest of the talk is on the change in social welfare. So the benefit of each of these policies, considering costs. So here is the baseline case. It is in the case A with low bus stop and payment technology. And what you see there is we have a reference scenario where the bus stop, the bus system is self-financed, there is no car congestion pricing, and there is mixed traffic. And I'm going to show you first what happens if you implement the optimal subsidy, optimal car congestion pricing, and a bus corridor without investing in road capacity as a reference case. So what you see there is the 3 policies and the benefit they bring, the social benefit, the change in social welfare, accounting for the cost of implementing each policy. So for instance, the car congestion pricing, half of the revenues go to operate the system, and that is being taken into account. So what this graph shows is that for an average or representative European city, the best policy is to implement optimal car congestion pricing. It's the one that gives the most benefits. Now, the optimal subsidy in this case, it's 100%. It's what it says over there, sub-ref 100, and it means free buses. That's optimal. And it gives less benefit. The third option, using part of the capacity for a corridor, the current capacity, the DL column there, is the second best policy in terms of standalone policy. So the best thing you can do in a European city, implement optimal car congestion pricing, then the bus corridor, and last, the optimal subsidy, which in this case is 100%. This was is analyzed in a little bit of more detail, but for London and for Santiago in the previous paper, this is a representative European city. And now, the interesting part is to compare what happens if instead of implementing any of these policies, the capacity of the road is increased optimally. And that's what I'm going to show now. And this is the 4th column there, cap. So it says the optimal increase in capacity, we let it be continuous. So it is 0.9 lanes, basically. And the benefit that it brings is almost the same as leaving the capacity for a bus corridor from the reference capacity. It is, so first, it increases welfare. Investing in road capacity as a unique policy, as a standalone policy, increases welfare. And this means that the Downs-Thomson paradox does not hold. This cannot increase welfare if everyone is worse off. And in terms of ranking, it is the 3rd best policy. So it is worse than implementing car congestion pricing, it performs worse than a bus corridor without investment, but it works better than the optimal subsidy policy. Now, what happens if this optimal capacity policy is interacting with the others? So this is what I'm going to show you now. Here you have capacity investment together with all the three policies separately that we discussed before. So road capacity and optimal subsidy is the fifth column over there. It says sub 100, which means again the optimal subsidy is 100, again free buses, and with less road capacity investment, 0.6 lanes. Then there's car congestion pricing along with road capacity expansion, which shows that it's almost the same. The optimal increase in capacity with congestion pricing is 0.1 lanes. So it's basically do not invest in capacity. With car congestion pricing is enough, and that performs better than the previous two: road capacity alone and capacity with subsidy. And the best policy in this case is on the right side. DL is build a corridor. So if you're gonna increase capacity, give it to buses. That's what this figure is saying at the end. The best policy you can implement is to build a bus corridor. Now, this is for the case A, where the bus stop and payment technology is inefficient. And let's see what happens if this is improved, and we look at case B. So again, before showing the results, bus and car speeds are low and quite similar across reference cases. So the initial speed in the reference for case B is almost the same as the initial speed for the reference in case A. Now, when bus stop and payment technology is improved, is efficient, we have this. So we move on the right is the same figure, but for case B. And when we move to this case, we see that all policies work better. The height of the columns is larger. So in addition to the direct benefits of improving this bus stop and payment technology, all the policies perform better. Second point I want to make is that if there is no capacity investment, so we look at the first three columns, the order of the policies does not change. So it is still better to apply car congestion pricing. The second best policy is implementing a bus corridor without increasing capacity, and the third one is the optimal subsidy. That is robust to this technology. Now, again, investing in capacity increases welfare. Again, the Downs-Thomson paradox does not hold, but also, again, it's not the best policy. And this is where we find a change. So, in case A, when the bus stop and payment technology is inefficient, the message is build capacity, but for buses. So build a bus corridor. Now, when this is efficient and the system works well when getting more people into the buses without building the corridor, then the message is improve bus stops and implement a policy to manage current capacity. Do not expand road capacity. In this case, the best option is implement car congestion pricing, as you can see on the figure on the right. So this speaks of the impact of the technology on strategic decisions such as pricing and investment policies. Now, to summarize a bit the results, we find that increasing road capacity is efficient by itself, but it's not the best policy. Second, bus stop and payment technology is key. It improves the benefits of all other policies. So if this technology is, the efficiency of this technology is low, we have incentives to invest in capacity, but for buses. And probably do something else additionally, such as car congestion pricing. Now, if this technology is efficient, it's better to implement congestion management policies and do not invest in capacity. So what matters is for this is not congestion, because all situations were equally congested, but congestionability. So how the bus system adapts or is able to receive more people. When this technology is low, then it is already quite congested, and the policies that without increasing capacity move people from car to buses are not as good. When this is efficient, then the system is efficient at receiving more people. Then you want to implement policies that move people from cars to buses. And the point is that one point is that this bus stop and payment technology is never seen as a strategic tool, but it affects strategic policy decisions. Whether you want to build, whether it is a good idea to build an urban highway depends on whether the bus stop and payment technology is sufficient or not. Now, we also test this with respect as a sensitivity analysis to the network size. So I'm showing now for the case A what happens if the system is larger, and we find that again the message is the best policy is to build a corridor, build capacity but for buses. And in this case is where we find what I showed you in the theoretical model, when with the optimal route capacity, the optimal congestion toll is 0, and the optimal subsidy is negative. So when the network is larger, when there's lots of people in buses and in cars, and the bus stop and payment technology is inefficient, you don't want to move people from car to bus. That's what this is saying. You already have too much crowding, too much queuing, bus queuing, and boarding queues. So it's not a good idea. The message here is just build a corridor. And in this way you improve the efficiency of the bus system. Now, if in the case with B, with efficient bus stop and payment technology, the message is again the same. So results are robust with respect to network size, in the sense that now it is optimal to manage road capacity and do not build. The best thing is to, before it was congestion pricing with a relatively small network size, and when with a relatively large network, then build bus corridors. Don't build bus corridors. Use the current capacity to have a bus corridor. So if the network is large enough, you can use a share of that network, give it to buses without construct. Now, to end this, some preliminary results for the US city. We find that building capacity improves as a standalone policy. So it performs better in a US city than in a European city. And it can even surpass management policies at reference capacity. Nevertheless, still with low bus stop and payment technology, the best you can do is build corridor for buses, but in this case also a bit more for cars. And when this bus stop and payment technology is efficient, we have the same conclusion. Do not build, implement congestion management. And this is the end of the talk. Thank you very much for your attention, and I'm open to question, comments.